There was once a time that movies were silent except for the music that was played with them. Then, sound came. This film takes a close look at the sounds we've always taken for granted. Vibrations are the source of all sounds. It's not hard to believe the drum vibrates, but what is the source of this sound? The bow causes the string to vibrate, and this generates the sound. Vibrations in the gong have enough energy to keep this ping-pong ball bouncing. We'll use the light from a laser to see the vibrations of a tuning fork. A mirror is attached to the end of the fork. As it moves, the reflected beam moves. The rotating mirrors provide a horizontal motion. The fork is electrically driven. We can see vibrations, and we can feel vibrations. But how do they reach our ears as sound? One small drop of water. Yet, its energy disturbs the entire surface as it moves out in waves. Energy from a vibrating object moves through the air in waves. When these vibrations in the air reach our ears, we interpret them as sound. What would happen to the sound of the bell if we removed the air around it? We're filling the jar with smoke. When the smoke is gone, most of the air will be gone. A pump is used to remove the air. The oscilloscope displays the sound of the bell. Without a medium such as air, there is no sound. Unlike water waves, sound waves travel in all directions. If you had a point source of sound, its energy would radiate like this. Let's look at a model of a small section of the radiating wave. We'll use this suspended spring to illustrate the action of waves in one plane. Waves can be created by both pushing and pulling on the spring. While the energy of the wave moves from one end of the spring to the other, any given coil simply vibrates back and forth. Let's analyze these sounds on an oscilloscope. 4.5 vibrations. 9 vibrations. And 18 vibrations. High notes have more vibrations per second than low notes. The number of vibrations per second is called the frequency. Without changing the frequency, notice the difference. The loudness of a note is related to the strength of its vibrations. We call this amplitude. Frequency and amplitude are two qualities of sound. But how fast does sound travel? The sound of this axe moves through the air in all directions. From a distance, the sound arrives late. How fast does sound travel? We'll use this abandoned track for our demonstrations. First, we measure off 300 meters. These flags mark the two positions. We'll use a starting gun as our source of sound. Up close, the smoke and the sound go together. Now, 300 meters away. Under these conditions, sound travels about 300 meters per second. Does sound travel through solid objects like this steel rail? If so, how fast? Let's find out. We can hear the hammer through the rail with a stethoscope. It seems to reach us almost at the moment of impact. In fact, sound travels 10 times faster through steel, which is a solid, than it does through air. Do you think sound travels through water? How would you measure its speed? A person with normal hearing can hear approximately 20 to 20,000 vibrations per second.
I understand you, but could you use better speech?
What's that?
That was better speech. It's a box.
Some people cannot hear sound as we do. For them, even learning to speak is difficult, since they cannot hear the sounds they make. This child is using a device to see the sounds of speech and then practice duplicating them.
Oh.
Good.
Oh.
Good.
Oh.
Good.
Oh.
Good. That was real good, Patrick. Which one do you want to do? Good. 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 Good boy, that's right.
Even people with good hearing cannot hear certain sounds. This dog whistle, for example, is too high-pitched for human ears. High-pitched sounds we cannot hear are called ultrasonic. Each of these metal bars gives off a high-pitched sound when struck. The oscilloscope can display even the ultrasonic tones, while all we hear is the tap of a mallet. One of the greatest pleasures we derive from sound is music. Musical instruments generate sound in different ways. But in every instrument, the sound comes from some form of vibration. Here, mallets strike the strings, setting up mechanical vibrations. We can also generate sounds by vibrating electrons in a circuit. This synthesizer can make a wide variety of sounds. Here, the keys are merely electronic switches. The shape of the wave, and therefore the quality of the sound, can be easily altered. These are all sounds of the same frequency and amplitude, yet each sounds different. The quality of most musical instruments is a complex mixture of vibrations. By analyzing these patterns, the engineer finds clues to the electronic combinations necessary to copy a sound. Here is the real cello. Notice the complexity within each wave. Now, the copy. The oscilloscope allows us to see clearly the difference between the two sounds. Sound can be music to our ears or noise. Our understanding of the physics of sound may help us diminish noise as a pollutant. Sometimes we can quiet a source of noise by simply changing the material it is made of. The metal garbage can makes more noise because it vibrates more than the plastic one. Here is another potential noisemaker. A good muffler, however, can reduce the noise. But how do you put a muffler on a jet plane? Engineers have discovered that certain frequencies of sound are more annoying to the human ear than others. Jet engines are now being designed to minimize these annoying frequencies. This particular aircraft is a lot quieter than other planes the same size. There are many positive steps we can take to quiet the environment, but it will probably never be as quiet as it was in the good old days. And even then, we were trying to use our knowledge of sound to make some things louder.